Welcome back to Mr. Hassan's Maths channel. I'm now going to answer question number 5 from this January 2022 unused paper. This is from the Pure Mathematics P4 International A-Level exam. This question is about vectors, and it says, with respect to a fixed origin O, the lines L1 and L2 are given by these two equations where lambda and mu are scalar parameters. Show that L1 and L2 meet and find the position vector of their point of intersection. So we have to show that they meet and find their point of intersection. So there's some questions I've done previously where it just says, given that they meet, find the point of intersection. And these two questions have different procedures. The question where it says, given that they meet, find the point of intersection, is worth less marks because you've got to do less steps, because you don't have to prove that they meet. You just have to basically show that they meet. So you have to just find the position of where they meet. So you have to assume that they do meet because you're told that they do meet, and then you can just use that assumption to find the point of intersection. All right. In this question, we have to first prove that they meet and then find the point of intersection. All right. So for us to prove that they meet, first of all, let me just dissect what this means. This is an equation of a straight line, basically in vector form. And the equation of the straight line is made of two parts. You have the position vector part, which tells you how to go from the origin to the line. So supposing this is the line somewhere going in this direction. So the first part of this is the position of any point on the line in relation to the origin. Okay, so this would be the position vector of a point on the line. How to get from O to the line. And the second part of the vector, which is associated with the scalar parameter lambda times, this part is the direction of the line. This is the direction in which the line is going. So say this is line 1 going in this direction. This is the point on the line that we're given, and this is the direction of the line. So part of this would be the vector 2 minus 3, 6. And depending on the value of lambda, when lambda is 0, you'll be here. When lambda is 1, you might be there. Lambda is 2, you'll be there. Lambda is minus 1, you'll be here. Lambda is a half, you'd be here, and so on. So depending on the value of lambda, that takes you along the line somewhere. So similarly for this, supposing I'm not drawing these to scale, of course. Supposing this is line 2. Okay, say this could be the point 13 minus 1, 4, which is a point on the line. And this could be the direction of the line, 5, 1, 3, for example. Okay, so there's a certain value of mu which takes you to different parts of the line. When mu is 1, you might be there. When mu is 2, you might be there. When mu is minus 1, you might be here, and so on. Okay, so there's going to be a point. We have to show that they intersect. So there's going to be a value of lambda and a value of mu, which will cause these to have the same position vector. That will take us from O to that point. Okay, so there'll be a value of lambda and mu which will make these two lines go to the same position. And that's what we have to do. We have to prove that they meet. Okay, so that's what we're going to do now. We're going to prove that they meet. We're going to find the value of lambda and mu which causes these two lines to meet. So what I'm going to do is, first I'll set up an equation. If they do meet, then there will be a value of lambda that I can substitute into here, which will cause this to go to a point which will have exactly the same I, J, and K components as this vector. So there's going to be a value or a value of mu which will take us to that same point. So we got to find the value of lambda and mu and show that it's true for all three equations. So what I'm going to do is I'm going to make 3 equations from the I, from the J, and from the K components. From the I component, I have 4 plus 2 lambda, and that has to be the same as 13 plus 5 lambda. Sorry, 13 plus 5 mu, and that's one equation. Another equation I can make from the second row, from the J components, I know 4 minus 3 lambda equals negative 1 plus mu. See, I already made a mistake. That's 5. Be very careful. 13 plus 5 mu. Be very careful. It's very easy to make mistakes here. So let's just make sure I've written everything with the signs as well. Okay, good. This is very, very easy to make mistakes in this topic. So you have to make sure you keep checking that you've written everything correctly. So negative 5 plus 6 lambda is equal to 4 minus 3 mu, and that's equation 3. So now you can choose any two of these equations to solve simultaneously to find lambda and mu. And then if that value of lambda and mu that you found satisfies the third equation, then you have proved that these lines will intersect. And then you can find the point by using the lambda or the mu value in either of these two, the lambda value in this one or the mu value in this one, to find the point where they intersect. So first I'm going to do is I'm going to use, I think, equations 1 and 2. If we take equation 1, I have 4 plus 2 lambda equals 13 plus 5 mu. And if I take the second equation and try and think, if I make this into 5 mu, then these two I'll be able to eliminate simultaneously. I'll take equation 2 and multiply it by 5. In this case, that will become 5 mu, but then I have to multiply everything by 5. That becomes 20 minus 15 lambda equals minus 5 plus 5 mu. So now I can take these equations and I can subtract them. So if I subtract them, I have 4 minus 20, which is negative 16. 2 lambda minus 15 lambda, which is 2 lambda, plus 15 lambda, which is 17 lambda. I've got 13 minus 15, which is 18. I've got, these will disappear, 5 mu minus 5 mu, 0. That's the whole point of us doing this. So now I'll have 17 lambda is equal to 18 plus 16, which is 34. So therefore we can say lambda is equal to 34 over 17, which is 2. So now I can use equation 2, which is 4 minus 3 lambda equals minus 1 plus mu. And I can find what mu is by substituting 2 in here. So I have 4 minus 3 times 2 equals minus 1 plus mu. 4 minus 6 is minus 2 equals minus 1 plus mu. So add 1 to both sides. I have minus 1 equals mu. So I have lambda equals 2 and mu equals negative 1. Now, if those values satisfy this third equation, then I know that for sure these two lines intersect, because I've got a value of lambda and mu that takes us to exactly the same place in both cases. So when lambda is equal to 2, let's put when lambda is equal to 2 and when mu is equal to minus 1. Here we have the left hand side and here we have the right hand side. We have minus 5 plus 6 times 2, and this side we have 4 minus 3 times negative 1. That's minus 5 plus 12, which is 7, and 4 minus 3, which is 7. So we can say that they're both equal. Therefore, lambda equals 2 and mu equals minus 1 satisfy all three equations. Satisfy all three equations. Therefore, the lines intersect. Okay, we got to find where they intersect, so we can choose any one of those two lines and we can use those to find the point of intersection. Okay, now, so here we have the two equations, line 1 and line 2. Now we know that lambda equals 2 and mu equals minus 1 will take us to the point that we need. Lambda equals 2 substituted into here, so we could choose either of them. So for example, let's put lambda equals 2 into here. We have 4 minus 5 plus 2 times 2, negative 3 and 6. That's going to give me 4 plus 4, which is 8. 4 minus 6, which is negative 2, minus 5 plus 12, which is 7. Okay, that's we can use line 1. We could even use line 2 to check if you wanted to. If we use line 2, then we're gonna basically put mu as minus 1 into this. So we have 13 and minus 1 and 4. Minus 1 times 5, 1 and negative 3. That gives us 13 minus 5, which is 8. Minus 1, which is minus 2. 4 and minus 1 times minus 3 is plus 3. 4 plus 3, which is 7. As you can see, they take us to exactly the same place. I don't have to put them into both. I don't have to use lambda in here and mu in here. I can choose only one of them. I'm just doing this as a check, okay, to make sure I haven't made a mistake. All right, so we can say for sure it tells us to find what the position vector of the point of intersection is. So that means we've got to find the vector from O to A. which is basically 8 minus 2, 7. A is where they intersect. So it's 8 minus 2, 7. That's the position vector of where they intersect. Sometimes they say find the coordinates, in which case you'd write it in this form. 8 minus 2, 7. That's the coordinates of A. But the question doesn't ask us to do that. It asks us to find the position vector of A. So there is the answer to that question. 8. Okay, now for part B. Find the acute angle between line 1 and line 2, giving your answer in degrees to 1 decimal place. Okay, now in this question here, we got to find the angle between these lines. So the things that we're concerned with in terms of the equation of these lines are the direction vectors, which are these two. The direction of the direction vectors of the lines determine in which direction they're going, and therefore will determine the angle between the two lines. So supposing, say, this is line 1 and this is, say, line 2. All right, and let's say this is going this way and this is going this way. Could be going either way, but basically the angle between the two vectors is the angle when they are tail to tail. When they are tail to tail. Okay, so this angle theta is the angle when they're tail to tail. It could be that line 1 is going like this and line 2 is going like this. This could be theta, this could be theta. We don't know until we calculate it. All right, so just say we have this as theta. We don't really know. We'll find out when we work out the angle. So the theta is the angle when they're placed tail to tail. Now they want us to find the acute angle. Now if the angle theta turns out to be acute according to how these vectors are given, and then we leave the answer as it is. If it turns out the angle theta is obtuse, then we do 180 minus the angle to give us the acute angle between them. So basically, we know that there's a formula that the dot product of two vectors is always equal to the product of the magnitudes of the two vectors times the cosine of the angle between them. Okay, that's something that is true. Okay, that's an equation that we should know. So therefore, we can rearrange that to say the cosine of the angle between the two vectors when they're placed tail to tail is A dot B over the product of their magnitudes. So we know that the vector A is 2, -3, and 6. And we know the vector B is 5, 1, and -3. All right, so we need to find the magnitude of these vectors. And the magnitude of vector A is going to be 4 plus 9 plus 36, which is going to be 49. The square root of 49 is equal to 7. And the magnitude of vector B is 25 plus 1 plus 9, which is 10 plus 25, which is 35. So it's the root of 35. And I know that A dot B is going to be vector A, which is 2 minus 3 and 6 times 5, 1 and -3. That gives me 10 minus 3 minus 18. 10 minus 3 minus 18, which is equal to minus 11. 10 minus 21. Okay, so now I can say that the cosine of the angle between the two vectors is equal to minus 11 over 7 times the square root of 35. So therefore theta, now I know this is going to be obtuse now, because when you have a negative angle, it's going to be in the second quadrant. So what we're going to do now is we're going to find inverse cosine of negative 11 divided by 7 times the square root of 35. And that gives us 105.403. 105.403 continues on like that. So therefore the acute angle that we're looking for, this is not acute. If it was acute, that would be our answer. If it's not acute, it's 180 minus 105.403. So we take the answer and we do 180, take away the answer, and that gives us 74.596. 74.596 degrees, which is 74.6 degrees. That is the acute angle between those two vectors. So there's the answer to part B, 74.6 degrees. So that's part B done. Now we're going to go on to part C. Now part C says a circle with center A, and we know that those are the coordinates of A, and we also know that, and radius 35 cuts the line L1 at the points P and Q. Given that the x-coordinate of P is greater than the x-coordinate of Q, find the coordinates of P and the coordinates of Q. Okay, now I'm just going to draw a random line. Let's say this line 1. Okay, we don't know exactly what it is. I know that A is on line 1. How do I know that A is on line 1? Because A was the point where line 1 and line 2 intersect. Now, there's a circle with center at A. Okay, so let me just draw a circle. Okay, center at A. But make it a bit less thick than that. The center at A. Okay, and it has a radius of 35. Okay, and it cuts the line 1 at the points P and Q. Given that the x-coordinate of P is greater than the x-coordinate of Q, find the coordinates of P and the coordinates of Q. Just say this is P and say this is Q. Okay, say this is P, this is Q. All right. Now, we know that we want to find the coordinates of P, means we need to find the vector from O to P. Let's say this is O. Say this is O over here. This is the origin. So we need to find the vector O to P and the vector O to Q. That's what we need to find. Okay, now I know that P is on the line L1 and Q is on the line L1. And I know that the length of the vector from A to P, the length of the vector A to P is equal to 35. And I know the length of the vector from A to Q is also equal to 35. I know that because they've told us the radius of this circle is 35. I know P is on line 1 and Q is on line 1. And P and Q is where the circle hit line 1, right? So I also know that the vector from A to P is equal to some constant times the direction of line 1, which is this. So it's some constant times 2 minus 3, 6. And I know the vector from A to Q is the same constant but in the opposite direction. So it's minus k times 2 minus 3, 6. If I want to go from A to P, I've got to go k times 2 minus 3, 6. If I want to go from A to Q, I've got to go the same distance but in the opposite direction. It's along the same line, parallel. Okay, so if I can find that value of k, I can find what O, because I already know what O to A is. O to A, we already found the position vector of A, which is 8 minus 2, 7. So I know this vector is 8 minus 2 and 7. I need to find what the value of k is. Now I know I can do this, I guess, in 2 ways. Okay, I can do this in 2 ways. I think the easiest way for us to do it is to work out that the vector from A to P, exactly what it is. We know its direction, okay, which is 2 minus 3, 6. We know its magnitude. So let's say that, let's find the magnitude of the vector 2 minus 3, 6. 2 minus 3, 6, its magnitude is, I think we worked it out already, that's 4 plus 9 plus 36. Yeah, it's going to be the square root of 49, which is 7. Okay, so the direction of this vector is, the magnitude of this vector is 7. Okay, this vector here, 2 minus 3, 6. So if I know that the vector from A to B is 35 units, okay, and this vector is 7 units, then I can work out that the lambda or the k that I've written here is going to be 5. What we can say is, all right, let's do it in this way. Say that a unit vector in the same direction of this is going to be 1 over 7 times 2 minus 3 and 6. That's one vector. That's one unit in this direction. We want 35 units. So therefore, the vector from A to P is going to be 35 times 1 over 7 of 2, negative 3, 6, which is going to be 5 times this vector, 2, minus 3, and 6. So I know the vector from A to P is going to be 5 times 2, which is 10, and minus 15, and 30. And therefore the vector from A to Q is going to be minus 5 times 2, minus 3, 6, because it's going to be the opposite direction. So that's going to be minus 10 and plus 15 and minus 30, opposite. So therefore we can say that the position vector of P, O to P, is going to be O to A plus A to P. So it's O to A plus A to P. We know A to P now is 10 minus 15, 30. So I know this is 10 minus 15 and 30, this vector here. I know the vector here is minus 10, 15, and negative 30. So I know to get from O to P, which I have to find the position vector of P, I've got to go O to A plus A to P. So that's going to be 8 minus 2 and 7 plus A to P, which is 10 minus 15 and 30. So that's going to be O to P. 8 minus 2, 7, that's right. So you're going to have 8 plus 10, which is 18, minus 2 minus 15, which is minus 17, and 7 plus 30, which is 37. Okay. And then we're going to have from O to Q, which is O to A plus A to Q, which is the same O to A to O to A, sorry, 8 minus 2, 7. And this is going to be the same vector, but just opposite. So minus 10, plus 15, and minus 30, which gives us 8 minus 10, which is minus 2, minus 2 plus 15, which is 13, and 7 minus 30, which is minus 23. And there we have the position vector of P. Does it say coordinates or position vector? Coordinates of P and Q. So they want the coordinates of P and Q. So P has coordinates 18, minus 17, 37, and Q have coordinates minus 2, 13, and minus 23. And we see P is the one with the bigger x coordinate. Okay. Now, if it worked out that we ended up with this one, we called it P, having the, on this side, we can just switch the names around. But I could kind of guess that that would be the one with the bigger coordinate, because, when you multiply 5 by 10, you're going to get, by 2, you're going to be plus 10 on that one, and this one would be minus 10. So I kind of guessed it would be there. But if you worked it out, and what you called P has a lower x coordinate, then you can just switch the P's and Q's around and write that as, the other way around. So that's fine. That's the answer to part C, and that completes this question number 5 from this unused January 2022 paper. Other questions from this paper can be found in the playlist that will appear in this area over here. Other questions from vectors on P4 in this playlist. You can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.